So as you saw in the flyer today, we have Dr. Brorsen. He received his bachelor's and master's degrees in agriculture economics from Oklahoma State University. He got his PhD in Texas A&M, also in agriculture economics. He also has a master's in statistics of the University of Wisconsin. That's working in various areas in specific work in applied econometrics with emphasis in price analysis and futures and markets. Without more introduction, we're going to go ahead and get him started.
All right, thank you. Well, thanks for having me out here. I'm actually invited myself, and so that was nice that you let me come. I'm glad that Tennessee's treated my former student, Chris Boyer, really well. And it's a beautiful area, so it's a chance to come out here. I'm actually on sabbatical now. And so what I've got to give the presidential address this summer at the Western meeting, so this is practice, motivation for me to get started. So we're talking about the future of applied econometric methods, and there's a little more in the presentation than that, but let's go ahead and get started here. So this is an article that's in the Wall Street Journal this week. So talking about mathematics. So that calculus is so last century. Maybe we don't need calculus anymore, because really calculus, or differential calculus, there's like 10 rules you got to know. You can program them in a computer. And for integral calculus, nothing works anyway. And you got to do it numerically. So what do you need calculus for anyway? And they argue that we need training in statistics, which is pretty close to econometrics, linear algebra, and algorithmic thinking, which is also very much a part of agricultural economics, I would argue. And so I've always think of this, like micro theory. We take a lot of micro theory and learn all these Lagrangians and stuff. Production, I learned isoproduct curves, expansion paths, a lot of things that I've never used. And so what the talk is a little bit about is about econometrics. So econometrics, so are we teaching the right things? Are there different things we ought to teach? And just kind of start that discussion. So let's begin at the very beginning. So what are the goals of science? And people might argue that there's supposed to be prescriptions and policy stuff. Favorite question to ask at an interview seminar is, what are the policy implications of your work? And as if you didn't have any, you just did positivistic research, that wouldn't be useful. Well, and then I might argue that they could be to explain or to predict. But if you're an ag economist, based on the impression I get from reviewers, is we don't really care about predictions. We only want to explain. and so there's actually, as we'll talk about later, a branch that works more in prediction. And maybe should we consider that as part of ag economics or not? And so as we start with the basics of econometrics at the very beginning, start with the desirable properties of an estimator. So as in econometrics, we're wanting to estimate something. And so that's probably a number, and we're going to want to estimate it. And if it's a good estimator, what are its properties? And in classical econometrics, these desirable properties, first, unbiased, get the right answer on average. Best linear unbiased estimator, sufficient, has the lowest variance, consistent, or asymptotically efficient. And so this is the general part of econometrics. Now, there are people now that argue that we only care if they're consistent. We want to worry about the others. But consistency can be a very weak property. So econometrics then is about that, this is what we want, but what do we have? So in applied econometrics, we typically have observational data. It's not a designed experiment. Supposedly the gold standard would be to have a designed experiment. Of course, that probably really wouldn't work if you're dealing with people. So that's fine if you got some agronomy plots. But we have a lot of experiments with people, and they are imperfect as well. And so the data that we have as economists is you can think of it as data from a poorly designed experiment, or no experiment at all. And so we have this imperfect data. So econometrics is about how to get these properties back when our data are imperfect. So Lemur talked about the general problems with applied econometric work. And one of these is that there's a lot of whimsical choices to make. That if you correct for heteroscedasticity, there's a lot of different functional forms you could use, or different variables you could include. But it's also whimsical in terms of the functional forms that you use. Is normality itself a whimsical assumption? And that models can be fragile. So you get different conclusions when you use different models. And this also opens up the opportunity for pre-testing. And so that you can run a lot of different models and then just pick the one you like and report that. And that happens to some extent. Even recently, the psychology journals found out it was hard to replicate the stuff in their very, very top journals. It might have even been done honestly, but it was just kind of an anomalous result that was unusual, so it got in a better journal. And if you have too much of this going on, you can have slow advancement of science. And we've advanced a lot in science in the last 100 to 200 years. I've read the biography of John Adams. And John Adams and Thomas Jefferson were sharing a room. And they had a big argument over whether it was okay to leave the window open or not. That leaving the window open was going to make them sick. And so it's not all that long ago that there was a lot of things that we didn't know. And one of the reasons we've improved our knowledge is by following the scientific method and having good statistics. So I did just a little analysis of in the Western Association's journals. It was called the Western Journal of Ag Econ back in 1983, and now it's called the Journal of Ag and Resource Economics. And why did I pick 1983 as a year? Well, that's the year I got my PhD, so that's a nice relevant year. 2015 is the most recent. So just did a little analysis, compare the two. So what changes do we see in the journal? Well, one thing you see is that the pages is quite a bit longer. And so we're 19 pages now on average. This is journal pages. So what's that in terms of manuscript pages? Is that 45? It's a pretty big number. And so that's saying, don't send your short papers here. The number of equations has gone up, and a lot of this is in the conceptual framework. We still have a few papers that don't have many equations, but that's gone up. The number of references has gone up. Number 10, these are medians. The number of figures has gone way up. And why has the number of figures gone up so much? It's just technology. It's so much easier to do. So I would call that a good thing. Some of them you would do by hand, and it's hard for the publishers to take photographs and put in. And now it's so much easier to do that you see a lot of them. So what you see is an increase in complexity. We have this increase in complexity in the articles. I did an AJAE word search because this is an easy thing to do. Now the number of total things they count as, they're not exactly articles, has gone way down because they used to have a notes section. They used to print the proceedings that had discussions in there. And some years they print abstracts of the selected papers that they count as a separate spot. They had a lot of reports in there. And those have all gone away pretty much. Why did we take them out? Well, impact factors, because it hurts your impact factors. So we don't have any of those things anymore. And if you look just in terms of econometrics, it's gone up. Heteroscedasticity way up. Autocorrelation up. robust way up, Monte Carlo up, maximum likelihood, least squares down. Simultaneous down, partly because we do a lot less work with simultaneous equations, and also now we have a little trendier term for that, endogeneity, which is a little more general term. Probit or logit up a lot, and mathematical programming down. So we see that these changes in what we're doing as ag economists. In terms of the econometric methods that actually used, back in 1983, there was 2 papers that used descriptive statistics. Can you imagine that? You know, you won't even let a master's student do that anymore. You know, you got a great survey, and you've got all this data there, but you've got to estimate that probit model at the end so we can give you a degree. You know, you can't just have descriptive statistics. You got away with it back then. And 2 of them used ordinary least squares. Can you imagine that? And then non-linear least squares, probit, logit, Box-Cox, iterative single unrelated regression, and estimated generalized least squares. And when I graduated with my PhD, I knew all those methods. I could do all that. And we look at what we have now. Well, we've got 2 with quantile regression, 1 with a Garch M. We can't use regular probit anymore. We have ordered probit, which isn't that big of an advance. But we got fractional logit, 0 inflated Poisson, nonlinear 3, which is still sort of old stuff, asymmetric VAR, and this I don't know, that's dating stuff. MIMC logit or something like that, whatever that is. And so you know, we've got a lot of different things up here now. And you see we'll call them more advanced methods, or I might just call them gimmickier methods, you know, that we've got to have these fancier gimmicks. I mean, you can't just do logit, you got to do some variation of it anymore. And you think that, look at all this stuff, and how much of this is actually taught in our econometrics classes anymore? You know, you know, there's a couple things up there that I don't even know. So how am I going to teach it? And so you think about that we've got so much more to know now than we used to, and we see some pretty big changes here. So I've also looked at the JARE econometrics articles, and we see that the portion using econometrics has gone up. It's still not dominating. There's actually they had 3 articles in here that had nothing empirical. Imagine that. Ag economics article with nothing empirical. Now, what the biggest difference is in the number of observations. So the median observations was like 48 back then, and now it's 114. That's a big difference. So even though a lot of these were primary data surveyed back here, the sample sizes were still pretty small. And now we have many more observations. How does that address some of the problems that we talked about, that Lemur talked about? We wrote about let's take the con out of econometrics. So if you think about why have people done this, George Davis talks about, I've heard him talk about when he was in grad school, and he would sit at the computer running program after program, telling himself, be significant this time, be significant. And so that's one of the reasons he said he went to work on generic advertising, because he'd have monthly data and have more observations. And so that he could have some confidence in what he was doing. And you see that a lot of people have moved that way to change in the unit of observation. If you look back in '83, a lot of the work was done with aggregate data and annual data. And you're estimating supply elasticities and demand elasticities. And that's what a lot of the work was devoted to back then. And you don't see that near as much anymore. Maybe we either found out what they are or we've given up trying to estimate them. Or we consider that beneath us as researchers. So that's the big difference. And so instead of having U.S. averages, people might use county level data, cross-section time series. But also the cross-section data has gotten a lot larger. The number of observations and surveys has clearly gone up, which I'm going to argue as an econometrician that is a good thing. Primary data, not a big change. Misspecification tests, not a big change. It used to be very common to include a Gardner-Watson statistic, and now we don't always do that. The robust estimators I expected to be a little more than I found, and the bootstrap we found a few. So not wild differences in terms of hypothesis testing. So the possible drivers of the change. One is certainly the impact factors, importance of that in terms of a ranking of publications. For those of you not familiar with it, it's that the number of citations divided by the articles published for the last 2 years, but it has to be a certain category of citations in the Web of Science. And because of that, that has probably helped our articles get longer. And we've published a little more complicated stuff, so we can get more citations. The maturing of the field, that it's normal that as the field of study matures, that it becomes more mathematical and more complex. That's a normal thing to happen. And certainly the technology, because we have data collection that's much less costly. Surveys can be done at much lower cost. Analysis is much lower cost. And we have better graphics than we used to. It used to be pretty impractical to use some of these fancy methods because they weren't already programmed in the computer. You couldn't just point and click and get what you wanted. Whereas now with all kinds of things are available in R. So the current trends, this is really getting to the outline of what I want to talk about, is the generalized method of moments or robust standard errors methods where you say that, well, I just want to use a consistent estimator and I'll fudge my standard errors till they're right. And you can do a little better than that. Talk a little bit about what I'm going to call mostly harmless econometrics, because that's what the book's titled, but that's become a lot of interest in that. Talk a little about data science, machine learning, a little bit about Bayesian methods, and then finish up with talking about big data. So this is mostly the outline from my talk. So I'm going to start talking about hypothesis testing. There's an article called The Applied Statistician's Creed. And then this one of the things he argues is that all null hypotheses are false. That no coefficient is ever really zero. Because if it was really zero, why would you ever test it? I mean, no, it wasn't really zero. So all null hypotheses are false. So then, why do we do hypotheses at all? There's a journal that has banned hypothesis testing. Just better ban. No hypothesis testing in our journal. And, well, what does a t-value measure? Well, a t-value is essentially a measure of sample size. Really, mathematically, it's right there. And so I would argue that a t-value, when we do our hypothesis test, we're just saying, do we have enough observations that we can be pretty sure we got the sign correct? And that's usually what we're doing with a hypothesis test. We're not really thinking the coefficient's ever really zero anyway. And that's why we usually don't accept null hypotheses. You spell rejected. And what we find if we look at our journals, that asterisk econometrics is still common. When I read my students' papers, I still see this a lot. So what am I saying? Well, you know, usually we put a little asterisk if the coefficient is significant. And so when you read the paper, it basically says, the results section says, this coefficient has an asterisk by it, and this one doesn't. And that's the results section. And so, you know, that's not really what, the focus really isn't on the asterisk. Oh, yeah.
So do we think that people do that because we didn't learn any better when we took econometrics classes in school?
No. Why do people do that?
Well, just because there's that recent discussion from the American Statistical Association about, you know, using a p-value equal to 0.05 as sort of a criteria of whether, you know, determining whether a hypothesis is rejected. But in that same discussion, they said, well, people do this because that's what we learned when we went to school. We learned that that's sort of the critical cutoff, the p-value, and if we don't have that, then we can't really say anything definitive about, you know, our model results.
Okay. Well, and that's,
it seems like if we start, you know, we just started from day one with intro econometrics, you know, go through graduate school saying, you know, we don't care about, you know, just sign econometrics, or I guess asterisk econometrics, that would be even worse. And just started off by saying, well, here's how we interpret, you know, this, the magnitude of the coefficient in a meaningful way. And we probably would not do this when we become researchers.
Okay.
Or either that, or we teach students to do it right and they're just lazy.
I don't know. Well, one of the other things that Lemur talks about is convention. And so, why do you put t-values in your paper? Is it just because everybody else does? Or that you really think for information? And now, why do students tend to write about, put the focus on the hypothesis test rather than the estimate? I think it's just because it's easier. Way. You know, I'm not careful. I might write my paper that way. I'm lazy. But yeah, we could always do a little better job of teaching that. I'll agree with that. But anyway, the estimates are the goal, not the hypothesis test. And so that's why I'm not as big on the G&M kind of stuff as the economists. So I want to talk about robust standard errors. And I'm going to claim that they're becoming ubiquitous in economics and finance, not so much in ag economics. And if you go over to agronomy, you're not going to find them much at all. And so some argue that, well, estimates are consistent, but not asymptotically efficient. Consistent is good enough. And if your sample size is big enough, consistent is good enough. And so students, what are they always going to ask? Well, obvious answer, well, how big is big enough? And as any economist knows the answer, right? It depends. Of course, that's always the answer. But we're getting sample sizes, especially sometimes in finance, where you've got this intraday data, that you're getting huge numbers of observations where maybe consistency really is enough. But one thing, you know, I get a lot of reviewers telling me, well, you need to redo this. You've got to have cluster robust standard errors, you know, or something like that. And I don't think there's any big gain to it most of the time. What happens when you correct for spatial autocorrelation, for example? People think that's a big deal. You correct for it, your t-values go down 5–10%. And if you got enough observations, it's not really going to change much. But so I'm still, you know, I'm a classical econometrician. I'm still defending the old stuff. So I'm going to claim that this new wave of generalized method of moments that have kept the theoretical econometricians employed for the last 15, 20 years have a place. But I think that they're probably a little more dominant in some areas than they're going to end up. that a correctly specified maximum likelihood model is still always going to be superior. What's the other argument? Well, a correctly specified maximum likelihood model doesn't exist because you never really know for sure. And but it's in practice for an applied person, it tend to be pretty darn close.
So why do you think GMM will fade? Because like you just said, we don't know what specify the maximum likelihood function correctly, which gives rise to a more robust GMM estimator in cases where we'd use maximum likelihood.
Well, okay. As an example, I reviewed a paper recently that used GMM methods because that's what they were taught to do. And so, my comment was, yeah, this is okay, but your key parameter is not statistically significant. If you would just use normal methods and correct for heteroscedasticity the right way, I'm sure it would be. So they did it, and it was.
Well, and that's just changing the model because of the desired result. Maybe that's just a false positive.
Well, that's
I
a fair question.
I don't use GMM that much, but I just see it as if you're going to do maximum likelihood, fine. I usually do maximum likelihood, but GMM is good for, if anything, or maybe a robustness check in the maximum likelihood. Especially if you have a large sample size, you shouldn't see, I guess, egregious differences between GMM and maximum likelihood.
You won't.
But there's still cases where you do.
Yeah. And
you would question whether that was right.
I can see the other side. And so, as you see adoption with a lot of things, you remember what you're talking about. Normal adoption is to go high and overshoot and then come back and level off at that level. But why do students love GMM? Why? Because you just click it and, oh, look, normality is gone, heteroscedasticity is gone. If you use the right one, random effects can be gone, autocorrelation can be gone, use the right version of it, and it's like magic. But it only corrects for a certain kind of heteroscedasticity. So much of the time, the heteroscedasticity might be a variable that's not in the model. It's not so good there. It's not really a replacement for everything. The other thing is that as ag economists, we often don't have these giant data sets. And so, in a sense, you can substitute restrictions of some form for observations. And so I think that it's probably a little overused at the moment. Well, I might be wrong, which is fine. Okay, but it's clearly a tool that we need when we talk about the set of tools that you need as an ag economist. It's clearly one of them you need in your toolkit. Basically, what do you use it for? You use it when you have lots of observations. The reviewer gives you about heteroscedasticity and it won't make a lick of difference. Well, then you use it. And you get rid of the complaint. And I want to talk a little bit about mostly harmless econometrics. And you could argue about the title. I know that our econ department has gone towards teaching this. And you see what's some of the focus behind this? Well, are you guys from econ? Okay, great. So,
but I'm trained as an ag economist.
Oh, but econ people, they go through fads. Things comes and goes. One time it was rational expectations. Another time, for a while, they all went co-integration. And at least the ones that I work with now, they're still heavily influenced by Freakonomics. And so they're going out there and getting these giant, usually cross-sectional data sets that somebody's collected. And what they're able to do, they're able to test hypotheses about really important topics. But it's kind of a stretch how they're really connected. So it's like you got this causal fact that you're interested in, but it may have actually had to go through 3 different steps along the way to get there, but you're able to check this correlation. And another place where I find this is really important is I've got a friend who's in human environmental sciences, formerly home ec. And he's been working for 30 or 40 years on spanking kids. And what they find is they find that if you go out there and survey people, that the kids that misbehave get spanked more. You find that. And so a lot of people argue that that means that spanking causes kids to misbehave. And my friend thinks it goes the other way, and that they have problems with their statistics. And so he's very interested in making these sorts of things. And so we're interested in making causal conclusions, and we have, as an economist, we think, oh, we just use instrumental variables. But really, if you get outside the world of supply and demand, finding a genuine instrument can be kind of hard when you have great confidence in it. And so people are develop these other methods, propensity score matching, regression discontinuity design. Well, they call it differences in differences, which is okay. But I think that these are an important step in the right direction. And that because, yeah, instrumental variables is great, and that was even started kind of from ag economics in a way, but it doesn't always take place. Okay, so why is this useful? We desire to make causal conclusions without a designed experiment. And that's one of the reasons, as ag economists, we typically have to have a conceptual framework to go along with our applied econometric model. That if we're going to make some sort of causal conclusion from statistics alone, that we're going to need some type of conceptual framework. So a designed experiment is the gold standard unless it involves people. So my friend in human environmental sciences, they didn't experiment. They wanted to see if educating parents could help reduce obesity among children. And so they did this designed experiment and had parents educated and parents not educated, and it was a long-term education process. Do you know what happened? The parents that had kids with no obesity problem dropped out. And so their correlation was more that the people that completed the education had kids that were more obese. So even though they had a designed experiment, they still end up with the same problem they always had with the selectivity.
Well, that's a different kind of experiment. I mean, that's a particular kind of experiment. You're talking about an actual field experiment for people that don't know that they're participating in an experiment. I think that is a gold standard. But then when people know that they're participating in an experiment, then there could be Hawthorne effects, there could be other things, sample selection, things that are going on there.
And I agree that designed experiments are the gold standard, but they're hard to do with people. Because it's hard to keep it secret. It's hard to, okay, like you run hypothetical experiments on your, well, people don't pay attention. They just click. And you don't always, hypothetical doesn't always agree with what they do. If you observe, they can change their behavior. So yes, it's the gold standard, but it can be kind of difficult to do sometimes when it involves people, because they will change their behavior. So clear instrumental variables can be hard to find outside of supply and demand. In supply and demand world, clearly instrumental variables have a strong place. But outside, it can be it can be kind of hard to say sometimes. So the conclusions, I say, with this kind of literature, I would argue that it's very much a welcome alternative to instrumental variables, that instrumental variables has a place. One of the sessions at the American meetings I enjoyed the most was they had Jeff LaFrance, a very good one, up there talking about how reviewers didn't like their instrumental variables paper. I just really enjoyed that. Oh, yeah.
So I guess I'm uncertain about what you mean here. When you do propensity score matching, you still need an exogeneity assumption, right? Which is called unconfoundedness, which is basically the equivalent to our conditional need assumption. If that one fails, propensity score matching identified just like standard OLS is not identified. So I'm not sure what you mean when you say that propensity score matching will be an alternative to instrumental variables.
Okay, I'll think about that.
The one thing I'd add there, because I don't do a lot of that quasi-experimental identification, one thing I think is important about it is at least if people are in that framework, they're thinking about how they're identifying coefficients of interest, which is a much different paradigm than I got when I was learning econometrics, in the sense that we were just throw a bunch of crap in the model that we think is relevant. Yeah. Maybe some of the variables will have some theoretical justification, but they're not directly linked to any sort of microeconomic model. And we just kind of interpret these, these estimates as they're meaningful in some way. But at least in this case, we're thinking about, well, what sort of variation are we using to identify this effect of interest, and thinking about the counterfactual and so forth.
But so it's a fair question about how well it even does. I think that's a fair question. I want to talk a little about data science and machine learning. So if you look at job announcements, you see a lot of these around that they've been pretty successful in marketing this. And so how does data science and machine learning differ even from what we do? So as the machine learning people would argue that regression is sort of a special case of machine learning. And they think of regression as only being linear. And so that you have learning, when you learn, that's when you estimate your coefficients. So they have different language to do much the same thing. And they've been very successful in marketing these. Like Nathan Thompson, who was a former master's student here, he interviewed for a job at Monsanto in their data science group. And most all the people there were computer scientists. And they approached this as that they just are interested in output, and they have this set of data, and they want to find the way that gives them the best prediction. And they don't worry that much about which variables to choose. And as some of us know, there's a reason sometimes people hire ag economists instead of engineers, because ag economists might tend to maximize profit, whereas an engineer might maximize output or sales or something like that. And there sometimes can be a difference in that. So, is machine learning regression with a highly nonlinear functional form? Well, sometimes. So which is a special case of the other? But most people would argue that the stuff we do as econometrics might be a special case of machine learning and data science. The data science would be a little broader, and the machine learning would be more what the computer scientists do. And the tools they use are things like neural networks, support vector machines, regression trees, random forest, boosting. Now these are probably a little more developed for classification problems, where we might use a local for those than they are for where you have a continuous dependent variable. But they've been very successful in marketing this. Like my master's thesis advisor told me, that he just really doesn't. He's just not convinced that this is going to work. So how can you just totally ignore the information you have about the actual process? How can you not do something about pick the variables that you put in and reduce those? How can you depend only on data to do that? And the answer, of course, is you can only do it if you have a lot of data. So some more things, actually, they're better developed for classification problems. They're used today in voice recognition, handwriting recognition, self-driving cars. So it clearly works well when the only information is the data. Relationships are highly nonlinear, and lots of data are available. So they have a place. As ag economists, how often do we have lots of data available? Sometimes. Are our relationships highly nonlinear? Sometimes. Is the only information we have the data? Rarely. Usually we know something more. So the questions I would have, one of the things that I tell my students is, econometrics goes better with theory. There's a reason you study theory. You need to know theory in order to do econometrics. It really helps with specifying your model, understand what's going on. So does data science need theory? And so I would tend to think that they would be, well, of course, I'm going to argue that there's a lot of companies hiring a data scientist that would be way ahead of the hiring an economist. But I used to argue that about there's a lot of companies hiring an MBA when they really needed an analyst rather than a manager. They would have been ahead hiring a master's level econ student. So should we include data science in the PhD curriculum? I don't know that I really have an answer yet, but I think that's a good question. Should prediction be a greater part of agricultural economics? Because as I see it, I've sent papers to journals. The editor said, "Well, we're not interested in this. This is prediction. You need to send that somewhere else." So those are questions. I'm not really going to try to answer them. We'll talk a little about Bayesian methods. So Bayesian methods, yeah.
About all the data that's coming in now in precision farming.
Mm-hmm.
It seems like that would be an ideal place for data science methods to be used.
You're not the only one. And I got some slides about that. I have my own opinion, but there's a couple companies working on that now, private companies. Okay, all right. And I've been called and asked to apply for a job at one of those, and I didn't. So anyway, so Bayesian methods, useful in estimating highly nonlinear models. Some of the models I estimate with maximum likelihood, I have trouble getting them to converge. And with the Markov chain Monte Carlo methods, with Bayesian, you can get them to converge. And if, in theory, they will answer, in practice they don't. But it shouldn't matter. It can consider parameter uncertainty, which can matter when you're making decisions. I don't know if you realize it, but a lot of the expected profit maximization we do is using what's called the plug-in method, so that we're only getting consistent estimates of the optimum level, because we're not considering that parameter uncertainty. And so I would say, even though Bayesian methods will continue to be great in theory and continue to play probably a small role, but when you have the highly nonlinear estimator, they're a little easier to use. So now finally the big data question. So I was going to go to a big data session this summer. I didn't get to go to it because they didn't have a big enough room. And so it's really popular, really trendy, like every other fad. It's kind of on its way up, and then it's going to overshoot and come down, and we're going to find a useful niche for it. So some of the definitions of big data, what is really big data? Some people would argue that the data are too big to fit on one computer. That means that you have big data. And so then you'd have to have software such as Hadoop that you can link multiple computers together in order to analyze the data. Some people would argue that big data means you have, and so you've got to fit those, like sometimes they have in genetics. And there's lassos is a method that's kind of trendy for that, which is really just a form of penalized least squares, but it's a form, we've had shrinkage estimators for a long time. It's a way that gives you a lot more zeros, so it's a little more popular. And then the real answer is, in a way, is that most of our data is not that big. Most of our data is not so big that we have to use these specialized things. Certainly we have data that's so big that it won't fit in Excel, or it won't fit in Access even. We have data that's that big, but it's typically going to be data that will fit on a computer. There's a few exceptions with some of the precision ag stuff. So I want to talk a little bit about precision agriculture. I've done some work in precision agriculture. My experience is that most of the precision agriculture stuff is that most is break even at best. And so that, yes, we can apply a different level of nitrogen to every square meter. Yes, we can vary the seeding. We have machines that can do that now. And so the technical ability is there. But the economics, what I've seen, is not all that strong. And why is that? Because of what we often call flat earth economics. So if you take, like I heard Terry Griffith talk about, seeding rate. So the seeding rate, I don't know, it goes from flat like this, it's pretty flat over an area. And so what does the Climate Corporation, one of these companies, do? Their recommendation for seeding rate kind of varies over this flat area. And they never really get outside of that. If you look at the work I've done about nitrogen applications, you find that the expected profit gets pretty flat. Why is it so flat? Well, even if you apply probably a little too much, some years you needed it. It does you some good. And then if you apply not enough, well, a lot of years you didn't need that anyway. And so that it gets really flat, it's really hard to tell exactly how much to apply. So as long as you get in this kind of window for nitrogen levels, that you're pretty good. Now there's some question about pH. There might still be some genuine advantage of that. So my prediction for big data, it'll follow the path of most fads. It's going to go up, peak, fall down, and there'll be some businesses in the successful. There's a big data company in Stillwater, Oklahoma, which is pretty successful. If you can do it at low enough cost, and that's the idea of these companies, is if you can do it at low enough cost, even a little bit might work. So to kind of summarize the past changes that we've seen in our applied econometrics work, is the biggest improvement is in more observations. We've got more data, so the asymptotic properties are there. There's less need to do or incentive to do pre-testing so that you get that statistical significance. You can put the asterisk beside the variable or the estimate. We have increased complexity in terms of pages, equations, tables, figures. We see ready adoption of new techniques. So that's like what I tell my students, well, this might be pretty good, but you need a technique gimmick in order to sell it. And you see that a lot of our people have been very successful in adding gimmicks to their work. And what are the implications for PhD curriculum? So do we need to change some of what we teach or not? So something about the future of applied econometrics, or the same in terms of increased complexity. I would say that there's opening for a letters journal in agricultural economics. That one of the principals always like is simplicity. And as you see that the profession is not going my direction. So I always like things simple enough I can understand them, and we're not always going that way. Do we need an additional PhD econometrics course? But there's just so much more to know than there used to be. You see a lot of econ departments have added, say, a separate time series course. But we haven't seen that much time series in our journals. So we have the weaknesses of whimsicality, fragility, and pre-testing will continue, even though we're overcoming some of this. And I would say that there's some opportunities for our PhD graduates in industry in the data science field. That's what I have.
Any questions?
Yes, I have.
Sure.
Given all this, what's your opinion on fields being hung up on identification? Since if you say that the coefficient is never quite equal to 0, I mean, then you also may want to say that the conditional mean assumption never really holds either, right? Yet it seems like that the main purpose of writing a paper is to make an identification argument stick.
Yeah, well, you know, what is that guy? Friedman or somebody argued, you know, that, you know, yeah, all our models are wrong. You know, but you want to give up and do nothing? Or not? But what is it? All models are wrong, but some are useful. That's the same. So yeah, that's true. Okay, all right. But Fox said that. So anyway, yeah, that's true. You know, no theory is absolutely right either. We still learn from it. So that doesn't bother me. But I would still agree that none of them are right either.
Yes, sir.
Oh, no, you've had enough. We'll let Dave ask something.
No, that's good.
So I'm looking at this, by Paris and Holloway.
Okay.
AJAE title is Keeping the Dream of Rigorous Hypothesis Testing. So where do you see, so that's 1993, given where you see these trends, is that statement due or dream?
I think I'm gonna try to write that one down and think about it and answer it. I don't know that I know an answer. What do you think?
I don't know. I mean, it's a tough thing to try to do. But a lot of the stuff that I've seen specify new classical dual profit function provider, input demand, supply, system. 95 times out of 100, and density is not satisfied, then you can use the Bayesian method to make it. So does that mean I'm kind of at a class on that stuff?
So I don't know that I have an opinion right now.
Question.
Oh, I was just surprised about your conclusion of the trend in increased complexity will continue.
Yeah.
Because, I mean, so one thing that I've noticed is whereas in a lot of fields in economics, the trend's been the other direction. And we're going towards these more robust, you know, arguably identified sort of models. And so we're getting rid of the highly parameterized maximum likelihood estimators and so forth in a lot of cases. exchange for more robust methods. But one thing I've noticed is in agricultural economics that doesn't seem to be the trend.
No,
And so you think that the trend's just kind of going to continue ignoring what is kind of happening in the larger discipline, I guess?
or I might want to reconsider it. I'll think about that.
Or is it that we are kind of like behind you guys? Like
Well, I
when you
don't know.
start decreasing complexity, we are still in the increasing complexity side of things. Because like when I was taking your class, there was like the discussion about we are so stuck on the, because it's a limited dependent variable, 1 and 0, then you have to use a limited dependent variable models. But what if you're not interested about predicting? Why not using an OLS? You know, which is contrary what we keep doing. It's like if it's a limited dependent variable, then there's no other way. So I wonder sometimes if we are behind the track. Like we are here and we are decreasing complexity, we're still getting up until we realize maybe we don't need that much complexity.
We're usually about 10 years behind.
I mean, I might think it might be the case, not that we're in different directions. We might be going in the same direction, but we're just behind.
Well, I hope that really happens.
I wonder too, like how much of this is sort of the insecurity of us as a profession that we kind of see. Oh, last month there was data mimic model in there. What in the world is that?
Which that was 1968.
Yeah,
It's been around for
right. Dane's too humble of a guy to claim it, but like, for economists, we see this. Look what Dayton did. We need to one up them.
That's only like 50 years ago, so that's still new for us.
Yeah. Right, but I wonder how much of this is like our own, maybe insecurity is too vulnerable of a word for us to say out loud. But well, look what that guy did. I need to one up him, and we sort of maybe push it to.
Pushing it because the journal sometimes push you to that. What if it's the data at that?
But the journal is just us.
Right.
I know, no, but the trend.
What
What I'm saying is like, as an ag economist, why decide to go for an ag economics instead of an economics? Although I have a bachelor in economics, because I like the idea that I can work with, not that you guys don't do it, but working with other disciplines when we have these big projects, working with the plant scientists, the guy from the biosystems engineering, that help us understand how the plant is growing. And why not, like, okay, the nitrogen parameter has to be positive or negative, or you have a quadratic production function. And instead, sitting with the other scientists that help you understand what's going on with the experimental data. So what, like adding that complexity so that you have a publication, or adding that complexity because the project needs it.
Well, sometimes I find whenever I add complexity, if I'm working, I also work with a lot of people in West Tennessee stations and across departments, and whenever I do something that they don't understand, kind of above an ANOVA table by years, they kind of freak out and think, I don't understand this. This is, I read up until the methods section and then I quit. I don't understand it. Simplify this. Yeah. But then I say, well, I can't because I won't get it published other than somewhere other than maybe Chronicle Journal or
a multidisciplinary journal.
And that that's not a great incentive. The incentive is a little higher, better. So I kind of pose the question. I'm like, I wonder as a group of we are the journal.
Yeah.
We review each other's work, and it's sort of this. I wonder how much insecurity it has. We got to one up the next guy.
Are there any other questions? If not,